And welcome back. As we go ahead and continue to dive in looking at recursion, let's go ahead and take a moment to discuss some of those recursive design techniques that we have already been using, but let's put a little bit more formality to it. So when we start talking about defining recursive methods, one thing that we as programmers don't want to have to do is to continually be aware of our stacks and suspended computations. We don't want to have to keep track of that. However, one of the advantages of using recursion is that it lets us kind of ignore this little detail, and we're going to instead make the computer do all that work for us. So if we remember, we had the method power that we had previously defined in recursion demo 3. And the way we thought of that definition was when we said power x comma n, that's going to return, of course, power x comma n minus 1 times x. And because x to the power of n is equal to x to the power of n minus 1 times x, this, of course, is the correct way to value our return statement, provided that the computation will always reach a stopping case. So, of course, we need that stopping case in order to end that recursion, or else it's just going to keep going. Now, what are those criteria if we have, for example, a method that returns a value? Well, first thing we want to do, so after we check the recursive part of our definition, making sure it's correct, all we need to check is that the chain of recursive calls will always reach a stopping case, and that the stopping case will always return the correct value. In other words, all you need to do is check the following three conditions are satisfied. First off, we have no infinite recursion. Remember, a recursive call may lead to another recursive call, which may to another, and so forth, but every chain of recursive calls eventually does have a stopping case. And each stopping case returns the correct value for that case. And for the cases that do involve recursion, if all recursive calls return the correct value, then that final value returned by the method is the correct value. Now, what about for void methods? Well, we can apply those exact same rules. If you show that your recursive void method satisfies the following criteria, then you know it performs correctly. Again, no infinite recursion. Each stopping case performs the correct action for that case. And for each of the cases that involve recursion, if all recursive calls perform the actions correctly, then the entire case will perform correctly. And let's pop over to Clips to take a look at a couple more recursive examples here, just so we can kind of wrap our mind around them. And so what I've done is gone ahead and have a very simple program that's going to have two different methods here. One adds up to the number, whatever you input, from 0 to whatever. And the other one is going to count the number of evens that exist within that range. So I'm just going to add a quick print line statement here so we can differentiate this when we have our output. It's system.printline. Let's say the number of even digits is, and we'll just add a semicolon. Let's give this a run. So first thing it says, enter a positive integer. All right, so if we want to enter in a positive integer, let's just do something real simple when we're testing this out. So we, of course, have two here. We have one called add up to num, which if you look, it's going to take in a integer. And our stopping case says if it is less than or equal to 0, return stop num, which simply just means return that number. So for example, if we plug in 1, we should expect, of course, it to just be 1. Otherwise, we want to return stop num plus, you notice here's a recursive call, plus add to num stop num minus 1. This is going to be a very common thing you see in recursion, is where you have like a -1 case. There might be some other examples, but a -1 is a pretty common thing you're going to encounter when you start working with recursion. Either it will be something like a +1 or something like that, but a lot of times it's a modifier very similar. If we look then at our count evens, again we have our stopping case, but this time you notice it says return 0. And that's because this particular stopping case, we want it to return 0 in this case because we have 0 as our number of evens. In our else statement, you'll notice we have a little bit more going on here than we have in some of our previous recursive examples. Again, we're calling the count evens method here, so we're saying stop num minus 1. But then we have an if statement inside of this that says if stop num mod 2 equals 0, we're going to increase this variable even count by 1. And notice that even count is defined up here outside the method. And that's a kind of interesting design choice, because if we have it inside the method, remember one of the things that might happen if we want to keep track of that count, what's going to happen every time we reinitialize that method. If we put it, for example, inside of here, every time we call that method, that variable will get reset. So it's a design choice that you have to consider when you're doing some of this method construction. Outside of this, of course, then we just return the even count. So going back to our code, which is waiting for us to enter run, it's always good when we're testing out to start with a small test case. So let's just say we want to enter in 3. All right, so we get our output, adding all the integers from 0 to the number. In this case, we get 6. So that's a very easy one for us to test because I can go 3 plus 2 plus 1. Oh, what do I get? I get 6. Okay, that works. The number of even digits is 1. Okay, that makes sense because if you think about if we're not counting 0 because 0 is neither even nor odd, that would make sense because the only digit we have is 2. Let's run it again, but now with a slightly bigger input. Let's go up to, let's say, 9. So we're going to put in 9 now, and we get adding all the integers from 0 to the number. So now we have 45. Well, let's think about it. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 is 45. Again, notice I'm not counting 0 because we just know it's not going to change anything. What about the number of even digits? Well, we have 2 plus 4 plus 6 plus 8. That's 4 even digits. So here it looks like my example of what I have is working. And again, just plugging in some of those small examples just to test it before we plug in something much larger. Let's just say we enter in something, let's say like 22. Now, of course, we should know for the second half, this is going to be pretty easy to do because, well, the number of even digits is just half of this. And of course, you could just try to work something that way. You could say, well, just take the number, divide by 2. That'll tell you how many even digits are. There are, of course, other ways that you can implement this, but this is, again, a way to do this with recursion. And with our adding one, obviously, that's a lot more complex. But by having some of those small examples, that's just another technique that we can use to test out our code. But you can see in terms of actual implementation, it's nothing different than what we've seen already with some of our recursive methods. We just simply are going to call them. These, of course, are defined as static, so I can easily just invoke them here within the main class. But other than that, this is the foundation for what we're going to be using. Now, we're going to use this to start introducing some new techniques that we can use, particularly when we start dealing with large sets of data.